Alrighty, so we have studied how to resolve vectors that create a right triangle when you know like 2 out of the 3 legs. But there's another method that you can use. It's called the component method. And for most vectors, there are some exceptions, but the components are the short legs of a right triangle. So that's a component, and that's a component. And if you know one side, specifically the hypotenuse, all right over there, and an angle, you can find the other 2 sides, just using your trig functions. So let's start with the sine function. The sine of 40 degrees is opposite, so I'm going to write opposite next to this one, because that's opposite the 40-degree angle, opposite over hypotenuse. And hypotenuse is 16 newtons in this particular example. The cosine of 40 degrees is the adjacent side over the hypotenuse. And tangent, probably not going to be a good place to start, is opposite over adjacent. But since we don't know either the opposite or the adjacent side, that's not going to be where we're going to begin. So what I'd like you to do is, in your graphing calculator right now, solve for opposite and adjacent. Ryan, what did you get the adjacent? Yep, 12.25. I'm going to keep a couple extra sig figs around. There's 2 sig figs here, and I'm going to force a second sig fig there. So using 2 sig figs, it would be 12, right? Newtons. And Mackenzie, did you get opposite yet? You saw that? What'd you get? 10.28 is correct. And if we're going to round to 2 sig figs, it would just be 10, right? Newtons. Okay. So those would be correct answers. And with 2 sig figs, it's 10 and 12. I want you to try something real quick. If we try checking this, actually, I'll just show you. 10 squared plus 12 squared, when you add them up, is 244. 16 squared, which would be the hypotenuse, is 256. That's a pretty big difference, right? So this is what I was talking about with trig functions sometimes, depending on how they round. And since we had to round down for both of these, the confidence limits made a pretty big difference here. When you square root this, it actually, I'm sorry, the 244, I think you come pretty dang close to getting 16 again. But watch what happens when we keep a couple extra decimal places around. So 10.28 squared plus 12.25 squared equals 256. So just as an illustration of sometimes trig functions can throw things off just a little tiny bit, okay? So why would we want to do this? Well, these vector diagrams are going to become really complicated. And if you can always take a vector and create or find the horizontal and vertical components, you can solve any problem. So if you know how to do this, you can do the most complicated problem that exists with vector diagrams, okay? So let me make it a little more complicated as an example. So let's say I have a 16 Newton vector, a force, pulling up and to the left, and an 18 Newton vector pulling perfectly horizontally, okay? And the 16 Newton vector is at a 49-degree angle with the horizontal. Now, yesterday, if you recall, we made a parallelogram out of two vectors that were not at 90 degrees, right? So we went kind of like that, and then kind of like that, made a parallelogram, and the resultant was the diagonal. But that's going to be inconvenient, because if we do that, we have to make sure everything is perfectly to scale, right? And you have to get out your protractor, and it's going to be kind of a hassle. So there must be a mathematical way to resolve this, and there is. What you will do is the 18 is good to go because it's already horizontal. You'll take the 16 and find the horizontal and vertical components. So if you would do that right now, just like we did in the previous example, we took the 16 and we found the horizontal and vertical components. Now we have just a slightly different angle, so go ahead and go. Tell me what you get. So smart and has such bad handwriting. All right, here we go. Tyler, what'd you get for these, babe? How about 10.5? Does that sound good?
Yeah.
Okay.
And then the opposite was 12.1.
12.1, okay. Very good. Those are all correct. Just about everybody had these, so nice job. If you can do that, so you just did the hard part. If you can solve for those sides, now you can resolve even the most difficult. So, I want you to ignore everything other than these two vectors right here, the 10.5 and the 18. If I said, hey, this is a conveyor belt problem, wherein you have, a conveyor belt moving at 18, these are newtons, 18, feet per second to the right, and you're walking on the conveyor belt backwards at 10.5 feet per second to the left, how would you find the final or the resultant or the speed relative to someone watching you? Subtract. So what do you get when you do 18 minus 10.5? 18 minus 11. 7.5, right? So that's what's left over horizontally, right here. It's about 7.5 horizontally this way, okay? 7.5 newtons horizontally. And the 12 or 12.1, we're just going to slide that over right here. That'll fit right in there, won't it? Because it's that same vertical. If I said you have a right triangle that's 7.5 horizontally, 12 vertically, could you find the hypotenuse? Use Pythagorean theorem? So go ahead and do that. Call that R for resultant. Jacob, do you have an answer for this one? You are correct, my friend. 2 sig figs, 14 newtons. Yay! Could you also find theta? Is theta going to be 49 degrees? No, probably not. Solve for theta, and then I'll let you take a lap. You're very quiet today. Maddie, did you get one? Did you get an answer? Not yet? Joshua, did you get it yet?
It's like 60 degrees.
Yeah, that's right. And this one, again, depends on like how many sig figs you use. I got anywhere from like, I'll just show you, 55, 59, 56 degrees. So yes, all of those would be correct. All right, so 55 to 60. Okay, it's going to get harder, so we better get up, take a lap, and come back. And Ryan, since I was mean to you, you get a sucker. Yes, you do. Yes. Yes.